know Tc, we can calculate this thermomagnetic limit. And what
Is it orbital?
No, it's purely thermomagnetic. You ignore orbital at all.
So is it so why do you ignore orbital? Okay.
It's an upper limit. You can't go over that.
No, this HT2, is it an orbital HT2?
No, it's that's experimental point. That tells you that superconductivity exists below that field. So, and then how you interpret it, that's a different story, and I'll talk about that. So, experimentally, if we see something like around 100 Tesla, and Tc is only 20 Kelvin, that tells us right away that the Zeeman energy is actually much greater than energy of the binding energy of the Cooper pair, the gap. The formula is H in Tesla is 184 times Tc in the BCS theory. So if we see something which is twice Tc,
but it's a single band clean material. There are probably corrections to disorder. It depends on disorder. It depends on the number of the bands. It depends on many things, right?
that's true. That's true. But okay, let me defer that question.
So
I'll talk about that.
in principle, you can measure the magnetic susceptibility and get a better estimate for this Zeeman limit from that.
Well, in fact, you actually don't even need to measure magnetic susceptibility. You simply equate the Zeeman energy to gap.
Yeah, but you can
that
get an
gives
idea
you-
of the magnetic energy associated just from the susceptibility, and then you can relate that to the condensation energy, and that gives you a better feel, perhaps.
That's true, but if you actually take into account susceptibility, that gives you even lower energy because susceptibility is pretty high here. This has a lot of permanent ions in it.
What exactly is the Zeeman energy?
Huh? Excuse me?
What's the Zeeman energy? What do you call
It's just Bohr magneton times H.
Okay.
So then what's unusual, the temperature dependence of the upper critical field is very anomalous. It has nothing like you would expect from conventional superconductor. It has a strong upward curvature in some materials. In some materials it doesn't. Or in some materials it looks more like a conventional two-band superconductor like MgB2 with upper critical fields maybe 5-6 times higher. The scale is just larger. Or in some of them it looks more like heavy fermion HC2 with a very distinct shape, and I'll talk about that too. Then basically within this family of peptides you can go from very classical behavior in terms of vortex dynamics. Let's say low Tc members of the family behave like conventional superconductors like niobium as far as thermal dynamics is concerned. The high AC materials like this guy behaves more like YBCO, like the cuprates, with a strong thermal activation of vortices, giant flux creep, vortex melting, and all these features you can actually see on peptides. And then recently we found that the response of these materials to impurities is very unusual. In fact, we can irradiate this with heavy ions and produce very uniform distribution of impurities, and the response is very unusual. Actually, these materials can tolerate a lot of disorder without strong Tc suppression. And that is really unusual given that the current models basically all assume that these materials have unconventional pairing symmetry. So let me first outline the phenomenology because I was asked by the organizers to give a long introduction. So this is a fancier picture of the peptides. You have iron arsenic plane here, sandwiched between two other planes, and this is basically rare earth oxide plane. So the rare earth can have magnetic moment or it can have no magnetic moment. For example, for lanthanum, there is no magnetic moment. If it's neodymium or samarium here, it has a pretty significant magnetic moment. The properties don't change much. So what you can see here is the phase diagram, and X is this one. So you can dope it, let's say, with cobalt. And you add holes or electrons depending on the material. And the phase diagram looks very similar to what we know from cuprates. First of all, for no doping, this is a diaphragmatic. But unlike cuprates, which are insulators, they are not insulators. These guys are semi-metals. So here, this material is semi-metal, and then there's a spin density wave with stability around 140 Kelvin. As you increase X, the Néel temperature drops, and then superconductivity dome emerges here. And also interesting that next to this entire ferromagnetic transition, there's also a structural transition, very close. This line actually shows the temperature of the structural transition. And this structural transition looks like this. Here we have a trigonal phase. As we cool down, it becomes orthorhombic and antiferromagnetic. So the structure goes from this to that. So this is a phenomenology of pnictides. They all have very similar phase diagram. It all emerges from spin density wave state, but metallic spin density wave state.
Is there anything like a pseudo gap in this?
Yeah. All this, well, it depends what you call pseudo gap. Because different people define it differently.
It's a
Maybe
fade
I'll-
gap.
Huh?
It's a fade gap.
Question.
Yes.
The semi-metallic nature, is it perfectly compensated?
No, it's almost compensated. In other words,
So there's very little gellium.
well, as I said, it's not perfectly compensated, but it's nearly compensated. So the whole conductivity, if you try to measure carrier density from the whole conductivity, you can get a very wrong number.
Okay, fine. But the volumes of the hole and electron Fermi surfaces are almost the same.
Almost, yeah, they're almost the same here, but not here.
Aha.
As you dope it away, and it
Okay.
becomes superconducting, and I'll show you that from the surface.
Mhm.
So, and people did neutron scattering, and they could actually find what kind of structure, magnetic structure is in underdome state. And it looks like this. It's entire ferromagnetic state, but it's like a stripe type order. You have spins going this way on one chain, and the other way on the other chain, and then they alternate. Also, they were able to measure the magnetic moment of the iron atom. It was very small, 0.3 Bohr magneton. However, it all goes away as we dope it. So as we dope it, this state disappears and it becomes superconducting. What else? Okay, so here, there's another interesting feature of these materials. There's a very strong sensitivity of the critical temperature on the angle between iron and arsenic bonds. There's this magic angle around 109 degrees, and then TC drops quite rapidly as we deform the lattice by applying uniaxial stress, for example. So what about Fermi surfaces and mechanisms? This is a very complex material because what happens here is this. If we consider the iron arsenic plane, here's an iron ion, and it has 5 d orbitals. And those d orbitals are hybridized with the p orbitals of arsenic. So generally there are 5 different bonds, and those bonds produce 5 different bands very close to the Fermi surface. And that is important to keep in mind because that can produce a lot of unexpected things. People did ARPAS, and ARPAS show the behavior similar to what ab initio people predicted. So if you look at the Fermi surface, you can see here a hole pocket. This is a hole pocket in the center of the beryllium zone. And there is also an electron pocket right here at the corners of the beryllium zone. Here, the size of the Fermi surfaces are very different. But if we dope it, and we move the chemical potential this way, we can always find the chemical potential at which the Fermi surfaces will be almost the same. And you can see that lots of bands actually are working very near the Fermi surface. So a small shift of the Fermi surface can produce a new pocket in and that can affect properties quite significantly. So those are Fermi surfaces of peptides. They look almost quasi two-dimensional, but the materials are not two-dimensional. They're actually only weakly anisotropic. Those are results of ab initio calculations. So you can see that there are 3 concentric cylindrical surfaces here and 2 here, 5 bands. For certain dopings, you can move this part to the middle, and it will be what people call nesting when the surfaces coincide. In which case you can expect structural instabilities and spin density wave instabilities, and many people believe that this nesting is what driving this entire ferromagnetic transition in the underworld state.
How do you define Fermi surface here?
No, those are calculated.
No, I understand, but you said there are 2 Fermi surfaces, 3 Fermi surfaces. What exactly is a Fermi surface in your terminology? Because myself, I'm used to not condensed matter systems,
okay.
whether it's one Fermi surface, you think, because...
No, there may be multiple Fermi surfaces.
So how do you define them?
Because if you have, let's say, let's consider time binding approximation, when you only consider coupling of nearest neighbors. Now, if this nearest neighbors have only one band, let's say the S wave, then you have only one Fermi surface. Now imagine that there are 5 of them.
Oh, I see what you mean.
Pointing
Okay,
at different names. And that's what they are,
Thank you.
because it's a D wave.
No, I understand. Okay, clear.
Now, right away people realize that conventional electron-phonon coupling can't explain DC that high. Because people can solve Liage-Berg equations these days very easily. So everybody can calculate or measure phonon spectra. So we know everything to calculate TC from Liage-Berg. And the calculations show that TC can be maybe 1 Kelvin or 2 Kelvin only.
So what kind of symmetry do these calculations predict? The gap symmetry?
S wave for the Liage-Berg, assuming conventional electron-phonon coupling.
So is it this sort of extended S wave when the...
Right, that's what I'm, yeah, but see, so in principle you can have 2 different possibilities. Now I said that there's a hole pocket in the middle of, in the center of the Brillouin zone, and an electron pocket in the corners of the Brillouin zone. Now, for the symmetry of the order parameter, we can have multiple scenarios. First, we can assume that it's just a conventional S wave. S wave means that there's a gap without the nodes, shown in blue. It just covers the entire Fermi surface. And then, if we take another pocket, it can also be an S wave. But then there are 2 possibilities. There might be a phase shift between the 2, let's say pi shift, or they'll have the same phase. In the first, if they have the same phase, then the sign of the order parameter is the same here and here. And that's called conventional S++ model. Now we can also imagine a situation when this order parameter is positive and this one is negative. They're both S waves. They don't have nodes. And that's what people call S plus minus. And this is probably the most popular scenario in this material, and I'll explain why in a minute. Of course, there are also other possibilities. For example, we can assume that on the whole surface we have S wave, on the electron surface we have D wave. And people have calculated this things using, let's say, an RPA approximation, and they found that the energy difference between this state and this state is very little. And the reason is that there are 5 different bands very close to the Fermi surface. So if you only move one a little bit, this state may have lower energy than that state. And people are even saying that you can change the symmetry by doping. So you start from certain doping, and you are in this state, and you can dope, let's say, go to the underdoped state, and the symmetry changes from this state to that state. I don't know any experimental confirmation of that, but that's what comes out from the work.
That would be 2 superdental transitions, right? On the right-hand side.
No, this is one transition.
But
It's it's like because this condensates on both Fermi surfaces are strongly coupled, so there's only one TC.
If you D wave on one part and S wave on the other, then you've got some mixed
Right. So,
representations.
what do you mean? Well, you can write down Ginzburg-Landau and you just take quadratic coupling.
Between D and S?
Yeah. No. Like psi1 squared, psi2 squared.
So the electron D wave state, if you rotate to other pockets, has
Yeah.
such that it's total S wave-like symmetry.
Yeah.
I
exactly,
see,
yeah.
okay.
There are four of those.
Okay.
So when you say it's mixed, so like in a single superconductor, you have
Yes.
both.
You may have. Let me be more careful. You may have. That's what people say. Or you can have what they call extended S wave, which has zeros but no sign change. In the D wave, you have plus here, minus here, plus here, minus here. In the extended S wave, you have plus, but nodes. Again, people who do calculations for living claim that energy differences are very small.
So if you have, say, some inhomogeneities in there, perhaps if
Possible.
they're moving around, they
Yeah.
could be one type in one
It's
part of the
possible.
sample.
Or you can have a structural defect and you might have this state on the defect and this state in the top. So, okay, let's forget about all these complications and consider the simplest two-band model, in which case you have Cooper pairing in two channels. You have diagonal coupling constants which describe you Cooper instability in each of them. And then you have interband coupling of diagonal coupling constants which actually couple this order parameter with this order parameter. All Cooper pairs have this zero total momentum, so there is no Cooper pair which consists of electron here and electron here. That would be no zero momentum which has high energy. So it's all conventional Q equals 0 Cooper pairs. The same can be said about impurity scattering. We have impurity scattering within this band, and then we can have scattering in this band, and there are also off-diagonal components who describe the scattering between these two. And right away people suggested that actually pnictides are the materials in which the off-diagonal coupling is stronger than diagonal coupling. That means that superconductivity comes from the interaction between these two bands rather than the Cooper instability inside each of them. So this is a very old slide. Actually, this is just a review of what people know about two-band superconductivity, which was discovered, the theory was developed right after BCS in '59 by American group and Russian group. And basically you have for TC, you have a BCS-like formula, except that this, what is under this exponent has a more complex structure. It's basically a two-level system. And so you have the interband coupling, and then you have interband coupling here and interband coupling here. And you can see that because interband coupling comes in this combination, the sign doesn't matter. I can change the sign, and I still have the same TC. However, what's important here is that this determinant can be either negative or positive. So this determinant is positive for a conventional two-band superconductor like MgV2, for which superconductivity comes from Cooper pairing in each bands, called pi and sigma band. And the interband coupling is weak, so this guy is small. In pnictides, way in the opposite limit. In pnictides, this guy dominates and this guy is small.
So why people are saying that it dominates? How is it know which?
Okay, next slide.
Oh.
So now that allows us to have superconductivity and repulsion. So let's write down the BCS equations for the superconducting gap. This is simply, this part is a simple gap equation, okay? Now, if you have two bands, we add interaction with the other band here. And then there are two couple equations for the order parameter. Now you can see here that if I simultaneously change the sign for lambda 1, 2 and delta, I'll get the same equation. Right? The equations wouldn't change. So that allows us to have lambda negative. And lambda negative in BCS language is repulsion. And repulsion is usually much stronger than attraction, because attraction only comes from phonons. And phonons are weak. Now, because the system is close to the antiferromagnetic transition, there are lots of magnetic excitations in the system. And those magnetic excitations result in magnetic susceptibility, which peaked for the Q vectors, which connects the center and the core of the Brillouin zone. It's like in Q rays. So then naturally you can say, okay, my coupling constant is nothing but the superexchange matrix elements times the density of states times the susceptibility, the magnetic susceptibility. And this comes from the RPA. It's like, you know, if you sum up the RPA letter, that's what you get. J is negative here because it's antiferromagnetic. So this lambda is negative, so that allows us to have repulsion, repulsive interaction, which can produce superconductivity. But the price to pay is to change the sign on the one of the Fermi surfaces. That's why people call it S plus minus. The effect of impurities is trickier because in the single band superconductor we only have two cases. We have non-magnetic impurities. Non-magnetic impurities don't affect TC. Magnetic impurities strongly suppress TC because if you scatter electron part of the Cooper pair of magnetic impurities, the spin flips and we break the Cooper pair. In a multi-band superconductor, we have more complicated matrix structure for the impurity scattering, and they depend on the band indices like 1, 1, 1, 2, and all that, plus there are spin indices here. So we can have intraband magnetic impurities and intraband non-magnetic impurities, interband magnetic impurities, and so on. And the results are different depending on the symmetry. For the S++, it's more like this. Intraband non-magnetic scattering doesn't affect TC. Interband magnetic, non-magnetic scattering only weakly suppresses TC. Simply because when I scatter one electron from one band to another, we break the Cooper pair in this band. But if the bands are the same, then the effect will be zero. There will be no change in TC. If the bands are different, then it will be a weak suppression. And then there is magnetic scattering, which strongly suppresses TC because you flip the spin. For the S plus minus pairing, the situation is more interesting because intraband non-magnetic scattering doesn't affect TC. Interband non-magnetic scattering strongly suppresses TC because now what happens when we scatter from this part of the Brillouin zone to that one, the sign of the order parameter changes. So basically when you scatter back and forth, we average order parameter to 0. It's like scattering on magnetic impurities. So scattering between parts of the Fermi surface which have different signs in the order parameter strongly pair breaking.
Can you think of this as changing the chemical potentials for the two?
No, it's simply this. You have, let's say, you have one Fermi surface and plus where the order parameter is positive and negative. So I have a Cooper pair here, and I scatter this to this. It scatters from plus to minus, and back. So when you average, you get 0. You average between +1 and -1, if the bands are the same. It's like scattering in the superconductor. You have plus here minus here.
You mean
scatter.
transition between the two, it's fast enough, so essentially you are-
Right, so if you scatter your Cooper pair from this state to that state, you change sign. So that is why scattering on non-magnetic impurities in the D-wave superconductor are also happening.
But doesn't this impurity scattering affect the position of the Fermi level?
Yes,
Shift
yes.
it up and
Yeah,
down
if you add
depending-
impurities, the chemical potential shifts.
Because then you see if you shift them in different directions, you can suppress pairing too.
No, I mean, we assume that you already have a given concentration of impurities, so your chemical potential is fixed, and then you just ask yourself what would be the effect of that concentration of impurity on this. Usually the shift of the chemical potential is not, well, it's important, but probably not as important as the impurity scale.
Another question for you. So in your phase diagram for barium iron arsenide, there's a large coexistent region of
Right.
magnetism and superconductivity. So my question would be if you think that the coexistence of both orderings would be also leading to similar arguments that you present, or whether magnetism changes something of the stability arguments you present.
Okay. That diagram I showed with the coexistent region is not universal. In other words, for many peptides,
Yeah.
the diagram looks like this. So they are not really
Yeah.
overlap.
I'm just looking for a specific example which I'm personally interested in.
Uh,
If you think for this example, is there any reason to believe that these stability conditions you mentioned are modified by the presence of magnetism?
could be. Yeah,
Is
that's
there some knowledge at least?
nobody knows.
Oh.
Because people claim that in this region where these two lines overlap, there's a phase separation. So you have regions, diaphragmatic regions, and then the superconducting regions, between superconducting regions. That's as much as people know.
So in other words, you just assume fluctuating the correlation of magnetism and you say...
Yeah, you can say that, but it's just the beginning because those materials are very young.
I have a question about S plus minus pairing. So you recover the Anderson theorem in some case, right? When
Yeah, intraband scattering always obeys the Anderson
But
theorem.
if I remember correctly, it's not only D wave which is suppressed by disorder, it's any non-S wave. So basically, whenever the scattering is not exactly the same as the pairing symmetry, it's Anderson theorem breaks down immediately.
Right, so
So
that's
how
an
can you
example, because in
Yeah.
a single band D-wave superconductor, scattering on non-magnetic impurities is separated.
Well, in any, so in P wave, in D wave, in any
Yeah,
wave.
but not in S wave.
Yeah, because the
Right.
symmetry of the scattering is the same as the symmetry of the pairing.
You can say that, yeah.
So, but I don't see how you could possibly have the symmetry of the scattering in S plus minus. So,
Okay, okay, here. You have S wave here and S wave here, okay? Now, here order parameter is positive, here is negative. Now, I'm scattering from here to here,
but what kind of impurity can do that?
non-magnetic.
So any non-magnetic impurity will
S wave non-magnetic impurities, if the Fermi surfaces are the same, let's say assuming that they're just identical, but one has positive and one has negative order parameter, then the effect of non-magnetic impurities on this, in this case, is exactly the same as the effect of magnetic impurities in a single band superconductor.
So they do suppress superconductivity.
Yes.
But I mean, what is the first line there? So what kind of impurity could restore the Anderson theorem?
Intraband. This is interband. This one is interband scattering. Interband scattering is scattering within this.
So, but it seems that you need to fine-tune basically some kind of disorder potential to even try to achieve
Well,
this.
see, in the model it's just a parameter because we don't know if you take, let's say, zinc, and people can calculate what part of the scattering amplitude produces intraband scattering and what part produces interband scattering. Then it becomes sensitive to the symmetry of the wave functions and all that. So, but usually a single impurity produces both intraband and
Yeah.
interband.
Yeah, exactly.
So,
That's what I
so the intraband component does suppress DC. Interband component does. But, okay. So, okay, we can calculate HC2 for the two-band model. I'm just showing you the equations so that you know that something actually can be calculated. But then you can forget about all these formulas and you can you can actually understand the physics using a very simple toy model, which is shown here. Instead of considering a two-band superconductor, let's just consider two thin films called them pi and sigma, connected by the Josephson junction. And this is a model of a two-band superconductor. This is band 1, this is band 2. And the Josephson junction models the coupling between the bands. Okay? Now let's apply the magnetic field like this, and ask ourselves what would be the upper critical field in this system. And what I showed here is this. Let's first draw HC2 for film 1 and film 2. Let's say like this. This is for this film, and this is for that film. Now if you turn the interaction on, they hybridize. And that produces upward curvature, as you can see here. So this curve was calculated using those big equations, but the physics actually can be understood in a very simple way using this toy model. And this toy model also shows that really doesn't matter what is the mechanism of superconductivity in each film. It just tells us that if there are two order parameters, coupled order parameters, then most likely you'll see something like this, simply because they interact.
What is the theta?
Huh?
Theta, what is the theta in this case?
Oh, yeah. This is angular dependence. Now, let's say this is a uniaxial material, and now we can rotate the field as a, relative to the c-axis. In a single-band superconductor, there is a scaling dependence of Hc2 on the orientation, and gamma is simply the mass ratio in the plane to the mass along the c-axis. This is a small parameter. Now, if you have a two-band superconductor, then the bands are different, so each of them have two different mass ratios. Let's say one is isotropic, one is two-dimensional. Very naively, but actually it's not quite that approximation, we can just take this Hilbert-Landau scaling separately for this film and this film. And that gives us a qualitatively right answer.
Has anyone tried an experiment on this?
Oh,
Just
yeah.
And they see the,
Yeah, actually it was all done on magnesium diboride, and people have sorted it out, then it doesn't work.
and then suppose you did 3 bands, could you increase it further?
Yeah, if you have 3 bands, then you have, I don't know, 20 feet parameters.
I understand, if you want to get higher HC2, right?
That is an important point, and let me come back to that later. So then, of course, because we're in a high magnetic field lab, we're obliged to do high field measurements on these materials. And this is a high magnetic field laboratory in Florida. Please, I welcome you all to come, but please do it maybe in October, not now. So this is the main MagLab building, and here we have the strongest magnetic DC magnet in the world, which can produce up to 45 Tesla in DC field.
Can you bring your credit card in?
Excuse me?
Can you bring your credit card in the building?
You can, but we don't guarantee you.
Okay.
So if that's not enough, there's always Los Alamos, represented here by.
A lot of things like
And they have pulse field facilities, which can go up to 200 Tesla. And that's what it looks like. We didn't try that.
what this picture shows.
This picture shows that basically you have a one-turn coil, and you have a bank of capacitors, and you basically dump all the energy in those capacitors into this turn. That produces huge magnetic field, but then the coil can evaporate. But then you just take another coil. So your sample is somewhere here, but probably you'll never see it again. But they also have a lot of, less violent magnets, which allow you to go up to 85 Tesla in the pulse. And then you can actually have several shots without doing this. And this is a very nice facility, and we use that. So the first measurements done at NHMFL showed very surprising behavior. First of all, that was the first measurement on lanthanum arsenic compound. And you can see that Hc2 is very high. See here it's 30 Kelvin, here it's 50 Tesla. And this blue line shows the BCS paramagnetic limit. Calculated just from the BCS model, on the condition that Zeeman energy equals the gap, the square root. So that's what it is here. And you can see that this line clearly goes over. And you can also see that conventional theory like Horkheimer, Hohenberg, and Horkheimer, Helfen, Hohenberg theory actually gives you Hc2, which is much smaller than this materials show. And Hc2 has a strong upward curvature. When we saw that, we realized that this thing looks very similar like that one. And this is MgB2, plastic two-band superconductor. Again, you can see a pronounced upward curvature for the field along the c-axis and the behavior like that in the AB plane. The behavior here was very similar. So we concluded that this is manifestation of multi-band effects. And we did more careful measurements on single crystals. This is neodymium-111 single crystal. And Hc2 values become so high that we couldn't measure them because we stopped at 60 Tesla. That was done in Los Alamos. The behavior was very similar. If you measure it along the c-axis, you have a strong upward curvature going like this. If you measure along the AB plane, it goes like that. Here the slope is about 10 Tesla per Kelvin. It's very high. In cuprates, we have only 2 Tesla per Kelvin. And I'll explain what it means in a minute. Angle depends, okay, let me start that. So, what can we extract from these measurements? Well, from this measurement we can extract the coherence length, which tells us about the size of the Cooper field. Simply, the Ginzburg-Landau theory tells us if we know the slope of Hc2 near Tc, we can calculate the coherence length. This is the flux quantum, that is Tc. For the numbers we have, we get something around 20 angstrom. 20 angstrom, that's what we have in cuprates. So the size of the Cooper pair in these materials is small. In fact, some of the materials show the slope. Here we took about 4 Tesla per Kelvin. I'll show you the cases when we have 100 Tesla per Kelvin. It's almost vertical. Then, from the resistivity, we can estimate the Drude mean-free path. We get something of the same order, telling us that the mean-free path is of the order of the coherence limit. So we can call it the Moradi-Dijoni limit, or Moradi-Cohen limit. Really, it's very hard to say what it means in terms of symmetry because we just don't have enough space, a field space, to distinguish between different pairing scenarios. For example, for neodymium crystal, all data points stop here. This is less than half Tc. So when we try to fit with different models, we can actually fit them equally well, simply because we don't have enough data points. However, people did measurements, and we did too, on peak tides which have smaller critical temperatures, and then we have enough data points, because we can actually go to 70 Tesla and measure Hc2. And what you see is it starts linearly here, and then it starts flattening. And this flattening is the first indication that paramagnetic effects come into play. So it's not just orbitally limited Hc2 like here, but at low temperatures, paramagnetic effects become important. However, all of them are well above the BCS paramagnetic limit. Again, that's how paramagnetic limit in the BCS theory is calculated. Zeeman energy equals the superconducting gap divided by square root of 2. So the same formula expressed in terms of Teslas and Kelvins look like this. HP in Tesla is 184 times TC in Kelvin. So if TC is 20 Kelvin, then paramagnetic limit will be smaller than 40 Tesla. And they can go up to 60 and 70 Tesla and still see superconductivity, like in all these cases. Here I simply plotted this line. And you can see that all data points cross this line. It's not anomalous because many materials have that. Even very conventional superconductors, like, for example, Chevron phases. But what's interesting is that this is HC2 along the C-axis, is HC2 along the AV plane. There is very little difference between the two. Here too, and well, there's a difference, but not a huge difference. And Fermi surfaces suggest that we should have two-dimensional highly anisotropic material. If we have a highly anisotropic material, then the difference between the field along the C-axis and along the AV plane should be large. Here it isn't. And that seems to suggest that maybe for these materials, the orbital pair breaking is not important, that maybe Zeeman pair breaking, that's what defined as HC2, and the Zeeman pair breaking is isotropic. Doesn't matter what direction the field is. Here I'm just showing that, again, there are lots of materials for which the paramagnetic limit is exceeded. This is Chevron phase. This is the paramagnetic limit. So you have a factor of 2 high HC2. And usually people understand it either take into account spin orbit effects or simply take into account strong coupling. In Eliashberg theory, the paramagnetic limit is enhanced by a factor of 1 plus lambda. Lambda is electron phonon coupling constant.
So is the G factor important for this? What kind of estimate?
No, the G factor, they say G factor is, well, people don't take it into account, please.
Why? It could be easily quite different from 2, right?
Well, at least in a simple model, I'm talking about here about very simple models. They simply assume that G factor is 2, then they plug it into Eliashberg equations, and from the Eliashberg equations comes this formula in which the paramagnetic field is enhanced by a factor of 1 plus lambda, and you can understand where's it coming from, like this. It has all these formulas when you sum up all Matsubara frequencies. And strong coupling limit, you multiply Matsubara frequencies by Z. Z is a normalization factor, and the simple model is just 1 plus lambda. So basically you multiply all temperatures by 1 plus lambda. And you get that.
But there are 5 Fermi surfaces here, so
No,
presumably
no,
5
it's
Z's.
a single band. This is
Model.
for no, this is for single band.
Model, but the
Model.
material is 5 band.
Oh yeah. This is a single band. Now, then if when we did measurements for this guy, again we're limited by 30 Tesla we have in Tallahassee. You can see that HC2 just starts almost vertically here. And what I did for fun, I took the curve for the Zeeman paramagnetic field calculated in 1963 by Sarma, which simply neglects orbital pair breaking and takes into account only Zeeman terms. And this curve looks like this. It fits perfectly from here to here. Unfortunately, we didn't have enough data points to say more. But later, people have done a lot of studies about on these materials, and again, they all show similar behavior. The slope here can be very high. So if we calculate coherence length from the slope, assuming Gizmo-Landau theory, you get coherence length maybe fraction of a nanometer, few angstrom only. We can use multiband theory to calculate the slopes, and here are the formulas here. This is HC2 for multiband theory. You have psi1 and psi2 in two bands. So it's really not that important. Because the biggest question is, first of all, why the slope is so huge? Because it shouldn't be in the conventional superconductor. And we did more, and this is the last experimental graph of HC2. I'm going to show, and this is for this material again, and the slope here, well, they put 500 Tesla per Kelvin, but really, we can't say it's high. It's almost like a square root behavior. And that seems to suggest that we have somehow the orbital pair breaking doesn't work at all. And it's strange because it's a semi-metal, so it should behave conventionally. Everything behaves conventionally, but the slope looks like this. And then it flattens, and then goes like this. So it is very suggestive that you have a full differential state here. Because this kind of behavior tells us that paramagnetic effects are very strong, and paramagnetic effects are very strong, then we have a full differential state in which let's say we have two bands. This is spin up and this is spin down. Now we pair this electron with this electron to form a Cooper pair, but because they have different momenta, they are not the modulus of this momentum is not the same as this one. Then there is a delta P plus minus P minus. So the Cooper pair has non-zero momentum. And this is a full differential state, and people have searched for this state for many years, and there were several talks about that last week.
To determine, could you image the surface or something?
Huh?
To find if it's one of these FF states.
What do you mean by image the
I
surface?
mean, wouldn't it have oscillations on the surface or something?
No, because it's, you really can't, well, if you have a good idea how to detect full differential state, I'll be happy to hear. Because all we can do at the moment is only to measure resistive transitions. So, and that's what they show. You can see that the shift, applying 7 Tesla only shift the curve by a fraction of a Kelvin. Those are real transitions. This is 7 Tesla, so it's less than, let's say, 0.2 Kelvin. We can calculate the slope from that. It will be 20, 30 Tesla per Kelvin. It doesn't really matter how do you define HC2 as a midpoint or as an onset or here. The curve just doesn't shift. And that's why the slope here is so high. However, if we compare these materials with heavy fermions, we find a remarkable similarity. And I just took a bunch of pictures from review articles for heavy fermions. You can see very similar behavior of HC2. It's almost vertical here, and then it flattens. Very similar to what I showed before, except that, of course, the scale is different here. Here you only have 5 Kelvin. For pnictides, you have 30, 40 Kelvin. And if you simply multiply the scale by the scale, instead of 20 Tesla here, you'll have 100 Tesla.
Is it also a Zeeman field they're talking about in the heavy fermions?
In heavy fermions, I think that's a common belief that in many heavy fermions, like for example, the full differential state was reported for this guy. At least that's a candidate for the full differential state. I think it's more complicated than that, but people did specific heat around here and find that there is a phase transition.
No, but the reason you have upper critical field, is it the Zeeman effect or orbital effect?
It's supposed to be orbital
Yeah,
effect, because
much
near
stronger.
TC, Zeeman effects are not important.
Right.
However, so what you're supposed to see is something like this. You're supposed to start linearly, like Dietrich Landau tells us, and then flatten like this.
But there are many other materials where this upward curvature is seen. For instance, in superconducting films, you know,
Sure. But see here, you can have a variety of different behaviors. So here, for example, you see the upward curvature. Here you don't. Here and here you have the behavior which is very similar to what I just showed for one of the peptides. Other peptides behave more like this. But what is really unusual, and I really don't know the answer, is that here the slope is almost vertical. It looks like if somehow the orbital pair breaking is not important at all. But the behavior is very similar for the heavy fermions and peptides. And if you think about it, it's not very surprising because this behavior in heavy fermions comes from the fact that the electrons are very heavy. So, you know, the coherence length is small. In peptides, the coherence length is small because the carrier density is small, because they are semi-metals. So they may behave similarly for different reasons. Okay, so here is a little more about the paramagnetic limit. I think I should speed up a little. Well, the question is always, what does it take to reach the paramagnetic limit? How do we reach paramagnetic limit? Well, the simplest way would be to add impurities, because as we add impurities, the coherence lengths become smaller and smaller, so HC2 goes up and up and up. And then, if we calculate HC2 from orbital limiting, it may be higher than the Zeeman field. And then Maki introduced the parameter, which is simply the ratio of HC2 orbital divided by, let's go to 2 here, divided by HP. And this parameter, if this parameter is large, then paramagnetic effect becomes very important. And if we express it in terms of parameters and entropy coefficients,
You can use invisible ink too.
huh?
You can use invisible ink too, it will be the same effect.
Okay, I'm sorry. Here, how about this?
Yeah, it's better.
So this is a superconducting gap. This is the Fermi velocity in the EV plane. This is the Fermi velocity along the c-axis. This is a bare electron mass, free electron mass. Now, normally, if you have a conventional superconductor, like niobium, isotropic, what is here is simply delta divided by the Fermi energy, which is always small. So we don't expect anything important, any paramagnetic effects in the conventional superconductor, unless the superconductor is dirty. So when it becomes dirty, then HC2 goes up, this one doesn't change, and then we can have some effects of paramagnetic Pauli effect. However, if superconductor is anisotropic, you see that it's inversely proportional to the Fermi velocity along the c-axis, and if the Fermi velocity is small, like in the 2D case, then paramagnetic effects become really important. Or, if we have very heavy mass. If we have a very heavy mass, then we can write it like this. And that'll be the band mass. Sorry, the other way around. So in heavy fermions, this ratio can be about 1,000. So this parameter can become larger. So that might explain why paramagnetic, Pauli paramagnetic effects are very pronounced in heavy fermions. But in pnictides, they are simply important because the Fermi energy is small. Okay, now let me show you another feature of these materials. Thermal fluctuations here are important, simply because the coherence length is small. And thermal fluctuations of the order parameter can be quantified by the so-called Ginzburg number. And Ginzburg number is simply the ratio of the thermal energy divided by the condensation energy per Cooper pair squared. So if this parameter is small, then thermal energy is small compared to the condensation energy, and the mean field works just fine. And that's the case for any conventional superconductors. If we calculate it for cuprates, this Ginzburg-Landau is no longer small, telling us that thermal fluctuations of the order parameter can dominate the behavior, which is indeed true. This Ginzburg number also defines the width of the resistive transition due to fluctuations. So if fluctuations are zero, then we just have an ideal sharp transition, normal state here, drops to zero, and then zero here. With the account of thermal fluctuations, the transition is broadened, and the width of that transition is proportional to the Ginzburg number times Tc. Now, if we calculate a condensation energy per Cooper pair using Ginzburg-Landau theory, that's what we get. We get KTc divided by Hc, thermodynamic radical field, and psi cube, it's a volume per Cooper pair. So condensation energy density times the volume per Cooper pair squared. And this is the ratio of effective masses.
So isn't it just Tc over E Fermi in a clean superconductor?
Not quite. I mean, it's because psi depends on Tc.
And 1 over conductance in 30 superconductor?
Right. Well, really it doesn't have any scattering times because it's thermodynamic quantity. So it only has Fermi velocity, carrier density, mass, and Tc. And the mass ratio on this order. So basically what you do, if you calculate the correction to the specific heat in the first Gaussian approximation, the fluctuation correction, and then say this delta Tc should be of the order of the jump at Tc in the Landau theory. That's how you get that. That's how it was actually calculated. But qualitatively, it's simply this kT divided by the condensation energy squared. Now, if you plug all these numbers, you can see that there's very strong dependence of this width on Tc. It's Tc to the fifth. Then it's inversely proportional to the carrier density Q. Now, if we simply double Tc from 20 Kelvin to 40 Kelvin, well, delta Tc increases by a factor of 30. So that explains why low temperature members of the pnictides family behave like conventional superconductor, whereas high DC members with Tc about 50 Kelvin behave more like cuprates. It's because of this. So we need to know the mechanism. Also, the mass anisotropy can strongly enhance Morris fluctuations, but it's mostly the carrier density, mass anisotropy, and Tc. There's no magic here. So for low temperature superconductors, the typical Ginzburg number is 10 to the minus 8, almost 0, so we can ignore thermal fluctuations. In cuprates, it can vary from 0.1 to 10 to minus 2. That already tell us that you can see significant effect because the width of the fluctuation region is 1, well, from 1 to 10 Kelvin. 1 to 2 pnictides have the Ginzburg number similar to MGB2, kind of intermediate state. 111 pnictide, which has the highest TC, has a Ginzburg number the same as YBCO, the cube rate. It's simply because of that. So you can actually model all the behavior from classical low TC vortex dynamics, let's say in this cube rate, and then you can go to the high temperature, to the effects expected from high DC cube rates for 111 compound, and one manifestation of that is vortex melting. So in cube rates, it's well known that vortex lattice melts well below HC2. Here's the phase diagram. This is the HC2 line. We have a vortex liquid state here, and as sketched here. And here we have some kind of vortex glass state with a random key. But this line can be significantly lower than HC2. And here's a formula which describes that. For 111 compound, that's what we have. We calculated this melting field, it's significantly below HC2. In the lower TC cube rates, here's the melting line, here's the HC2, they're not very far apart. Okay, this slide shows the similarity between cube rates and pnictides. Yeah, they have very similar phase diagram. Superconducting dome close to the diaphragmatic state, except that this one is insulating, this one is semi-metallic. Other properties are very similar. Now, let me show you the last result we got about the effect of disorder on the properties of pnictides. And it's usually very difficult to introduce disorder because we try to mix them with other things. The impurities usually don't dissolve uniformly. They can precipitate and form some second phases. So we did it by radiation. So what we do, we take the neodymium single crystal and irradiate with the alpha particle. And here's a little movie which shows what happens. There's an alpha particle hitting iron atom in the middle, and it kicks it out of the lattice side, and it pushes it somewhere here. Okay. So iron atom in a superconducting state has no magnetic moment. Now if I hit it and push it somewhere here, it actually acquires a magnetic moment simply because the iron has a magnetic moment. The free iron has a magnetic moment. So we don't know what fraction of the magnetic moment is recovered, but obviously some. Because magnetic moment can disappear due to Anderson, in the Anderson model explains how it happens. But basically when we kick it out of the natural environment somewhere in the middle, the magnetic moment is simply restored. So that cartoon shows that irradiation can produce defects which have spin. So we introduce magnetic defects by irradiation.
Why do you think you moved the iron and not the arsenic?
Well, because yeah, you can,
because then you will have the same effect here.
Right. In fact, we had this program which can calculate which one is displaced depending on the energy, and this program tells us that irradiation of 2 MeV alpha particles mostly affect neodymium, iron, and arsenic. It depends on the mass, which one is lighter. So iron has a moment, neodymium has a moment. We can also knock the neodymium out of its place and put it somewhere here. The result will be the same. Neodymium has a magnetic moment even in the superconducting state. So you basically bring magnetic impurities to the plane which superconducts. So in the end, what happens, we introduce magnetic disorder by radiation, in addition to the conventional non-magnetic disorder. And the nice thing about this experiment that you can do it uniformly, because if the mean free path of the alpha particle is longer than the thickness of the sample, then you do it uniformly through the whole thickness. And that's indeed the case. The mean free path for this energy is about 4 micron, the sample was about 1 micron thick. Now what happens looks quite interesting. You start from this is resistivity as a function of temperature. The black one shows unirradiated sample. It's the black one here. So as we irradiate, the resistivity goes up, and also this strong upturn develops. Really, the effect is quite significant because the difference between this point and this point is a factor of 3. It's not a small effect. And then you can see that TC decreases. TC is this point. So as we irradiate, TC goes down and finally it becomes 0. But already this picture shows something very unusual. What it shows is this. If you compare resistivity from here, here, and here, the resistivity increased by a factor of 3, 4, 5. Okay? That means that the mean free path is 3, 4, 5 times smaller than here. But the mean free path is already short. So all models tell us that when the mean free path in the S plus minus model becomes of the order of psi, TC should go to 0. And it really doesn't. Now we did a simple analysis. So this is one of the resistivity curves. What we did, we fit this part with a quadratic polynomial, like in the conventional thermal liquid, and then this extra was analyzed separately. Well, and if you plot this extra in a log scale, we have a straight line, telling us that this delta rho is simply logarithmic in temperature. And when we see something logarithmic in temperature, we immediately say, aha, it's Kondo effect. And that is not surprising because, as I said before, radiation produces magnetic moments, so you expect some magnetic scattering. Magnetic scattering produces this logarithmic upturn, so it's all consistent. And the effect is huge. However, something is unusual about this Kondo interpretation either, because usually if in Kondo systems, at very low temperatures, there's always a saturation, because magnetic moments, when we form the bound state near the impurity, then it cuts off the logarithmic divergence in resistivity. So here we can go down to 2 Kelvin and see no sign of saturation, so we can only speculate that probably in this system the Kondo temperature is called in 2 Kelvin.
Is it spin 1/2 impurity?
We don't know.
But if it's not spin 1/2, only 1/2 is free, so it's no.
Maybe that's the case, but at least all I'm saying is that we don't have any sign of, we don't see any sign of saturation in the experiment, and don't even see the change in the slope, or because even for a bigger spin, if you form singlet, at least you will see some change maybe in the slope, but we don't.
So that's why you're confident that it's a magnetic impurity being produced. So this would be why you're confident it's magnetic impurity being produced.
Well, it's only our interpretation. We're just saying that that's the best we can do. Also, this part is not quite conventional because here you can see that it decreases very rapidly. In a conventional Kondo model, there's a very long tail, which doesn't fit the data. But this logarithmic behavior, you can see, in 2 decades in temperature. So then we can calculate the scattering rates using the Wood formula. So this is a fancy way of writing down the scattering rates, delta rho, and this is moment penetration depth. The reason why we wrote it this way, because then the carrier density cancels out here and here using the Wood formula, and we only have scattering time. And that's what we need to calculate it from the models. Okay, so if I plot Tc as a function of delta rho, it drops like this. And we can calculate the critical value of this parameter, at which Tc goes to 0, it's 1.7. As I said before, magnetic pair breaking is very strong, and in conventional Abrikosov-Gorykov type theory, this critical value should be 10 times smaller. It's 0.17. If you treat scattering in the Born approximation. Then what we did, we used the same analysis to compare different materials here. So here is the red is our sample. This blue triangle shows MgB2. YBCO is this, the blue squares, and this is more conventional vanadium-free silicon. What it shows is that our pnictide crystal behave more like a conventional MgB2 crystal than the cuprate. And the cuprate is a lot more sensitive to the irradiation disorder than this pnictide. Even though if you believe in all these models, S plus minus and maybe mixed theory, you would expect behavior similar to YBCO. Instead, it shows behavior more similar to conventional electron forming superconductor. And that is really unusual. So how can we understand that? Well, as I said before, if we have equal gaps with different signs, we have pair breaking scattering and non-pair breaking scattering. Pair breaking scattering is non-magnetic interband scattering and magnetic interband scattering. And those are non-pair breaking. It's been shown that if you have sign change in the order parameter, non-magnetic interband pair breaking scattering is strongly reduced if in the unitary limit, when the scattering amplitude is large. And this is a formula, so you can see that if this is large and this is large, you actually cancel the main part. So that reduces the effect of non-magnetic scattering. However, the magnetic scattering can be reduced. In fact, it becomes only stronger. And that is based on old theory of Kondo effects in a single band superconductor. In a single band superconductor, the theory of the Kondo effect has been developed in the 70s. And the answer depends on the ratio. Basically, it's a Kondo temperature divided by Tc. If the Kondo temperature is much larger than Tc, then what happens is that the Kondo interaction screens this scattering, reducing the effect, the pair breaking effect. So then, if the Born approximation shown here is like this is point, then if the Kondo temperature is high, actually Tc is less suppressed. However, if the Kondo temperature is smaller than Tc, we have exactly the opposite. Tc drops faster than the Born approximation. Suggests simply because the Kondo scattering increases as we reduce temperature. The scattering amplitude grows logarithmically. So this is this curve here. So this is all for single band superconductor. And it's actually been seen experimentally. So this is well understood. So here is our puzzle. In our case, the Kondo temperature is smaller than 2 Kelvin. And our Tc is 40 Kelvin. So we're supposed to be here. So we would expect much stronger pair breaking effect by magnetic impurities. Instead, we see something completely different.
Is there any reason they might freeze due to interaction because you're near an antiferromagnetic transition or due to RKTY interactions? and just form some sort of a glassy state? And
Well, in peptides, you mean?
yeah, well, here in your experiment, actually.
In peptides, the peptides is a different story now, because here is probably the most interesting part. This is an electron-phonon superconductor. The electron-phonon superconductor, Cooper pairing is completely decoupled from the scattering. You have pairing due to phonons, scattering due to magnetic impurities, and they're independent. And that's how you get this. Now, in peptides, if you believe in all these models, pairing comes from the interactions with magnetic excitations.
Yeah.
Now, if you add magnetic impurities, we change that interaction. So the scattering can be decoupled from the pairing.
But if they're frozen to some kind of state, let's say they form an ordered state, they don't flip, the magnetic impurities don't flip, and there is no suppression.
Yeah, they don't. No, I mean, if you have a frozen, yeah, well, that we don't know. No, I mean, we see the strong effect. I mean, because we see, resistivity shows this logarithmic upturn, telling us that there is a spin flip. Otherwise, you wouldn't see this logarithmic upturn in resistivity. So we can only speculate that in this material, we simply add magnetic impurities, and they change polarization of the band which does the coupling. They simply enhance the susceptibility, you can say. And the coupling constant is proportional to susceptibility. So it's really a non-BCS situation.